friends, today we shall solve some problems on photoelectric effect, and before that note down some important formulas. Number 1, kinetic energy of emitted photoelectrons is equal to the difference between energy of photon and work function, that is K maximum equal to h nu minus h nu naught, where nu is frequency of incident radiation, nu naught is threshold frequency, or this can also be written as hc upon lambda minus hc upon lambda naught, since nu equal to c upon lambda. Next, maximum kinetic energy can also be written as K maximum equal to E phi naught, where phi naught is stopping potential or cutoff potential, E is charge on electron. Thus, maximum kinetic energy or cutoff potential can be calculated by using this relation. And this maximum kinetic energy, it is equal to h nu minus h nu naught. That is K maximum can be written as h nu minus h nu naught, or EV naught equal to h nu minus h nu naught, or EV naught equal to hc upon lambda minus hc upon lambda naught, where lambda naught is threshold wavelength. It is the maximum wavelength above which photoelectric effect is not possible. And energy of photon is given by E equal to h nu, where E is the energy of photon, h is Planck's constant, and nu is frequency of incident radiation. Also, maximum kinetic energy is equal to E minus phi naught, where phi naught is called work function. This phi naught is equal to hc upon lambda naught, or it is also equal to h nu naught, that is equal to phi naught, and E equal to h nu, or E equal to hc upon lambda. And half mv square maximum, that is maximum kinetic energy, can be written as half mv maximum square is equal to maximum kinetic energy, or this is equal to hc upon lambda minus hc upon lambda naught, or half mv square maximum equal to h nu minus h nu naught. And if we plot a graph of cutoff potential or threshold potential versus frequency of incident radiation, then the slope of cutoff potential versus cutoff potential or stopping potential versus frequency of incident radiation is a constant, and that constant is called slope. That is, if we plot a graph of cutoff potential versus frequency of incident radiation, then we get the ratio h upon E, that is equal to slope. Thus, to calculate h, that is Planck's constant, h equal to E into slope, or slope into E, where slope, it is the slope of cutoff potential versus frequency of incident radiation. These are the formulas. Pause video and note down these formulas. Okay. Now, first problem, calculate wavelength and frequency of photon of energy 2 electron volt. Here energy of photon is given and you are asked to calculate wavelength and frequency of incident photon. Given that E equal to 2 electron volt, convert this energy into joules. Solution: E equal to 2 electron volt given and convert it into joules, that is multiply with 1.6 into 10 to the power minus 19. We get 2 into 1.6 into 10 to the power minus 19 joule, that is equal to 3.2 into 10 to the power minus 19 joule. And also we know that E equal to h nu. E equal to h nu. Here E is known, that is given, and h is Planck's constant. Its value is 6.625 into 10 to the power minus 34 joule second. Hence frequency nu equal to E upon h, where E equal to 3.2 into 10 to the power minus 19 upon h is constant, that is 6.625 into 10 to the power minus 34. And it is equal to, solving we get 4.83 into 10 to the power 14 hertz or per second. And next, frequency. We know that wavelength lambda equal to c upon nu, or nu equal to c upon lambda, or c equal to nu lambda. It is the standard formula, c equal to nu lambda or phi equal to f lambda. Phi equal to f lambda. Here we have taken c as the speed of light in vacuum, and hence here lambda equal to c upon nu, that is equal to c is 3 into 10 raised to 8 meter per second speed of light in vacuum, upon frequency we have calculated 4.83 into 10 to the power 14, and solving this we get 6.211 into 10 to the power minus 70, that is 10 raised to plus 8, it is 10 raised to minus 14. We get 0.6211, or it can be written as 6.211 into 10 to the power minus 7 meter, or it can be converted into nanometer or angstrom minute, because generally wavelengths are expressed in terms of nanometer or angstrom minute. Therefore the point decimal moves up to 3 digits. We get 6211 into 10 to the power minus 10 meter. This is 10 raised to minus 7, and here we get 10 raised to minus 3, 10 raised to minus 10 meter, or it can be written as 6211 angstrom unit. Thus frequency is 4.83 into 10 to the power 14 hertz, and wavelength is 6211 angstrom unit. Now we shall solve next problem. Silver is irradiated with ultraviolet light of wavelength 1000 angstrom unit. A potential of 7.7 volt is required to completely retard the photoelectrons. What is the work function of silver? Here silver is irradiated or radiated with ultraviolet light of wavelength 1000 angstrom unit. Therefore wavelength is given, wavelength lambda equal to 1000 angstrom unit, it can be written as 1000 can be written as 10 raised to 3 into 1 angstrom, and it equal to 10 raised to minus 10 meter, and that is equal to 10 to the power minus 7, minus 10 plus 3. Return the photoelectrons. What is the work function of silver? Here stopping potential is given, that is 7.7 volt, and we know that the maximum kinetic energy of emitted photoelectron in electron volt is equal to stopping potential in volt. Therefore, maximum kinetic energy in electron volt is equal to 7.7 electron volt, because 7.7 volt, that is stopping potential, is nothing but it is 7.7 electron volt of maximum kinetic energy. And you are asked to calculate work function, and according to Einstein's equation we know that E equal to phi naught plus maximum kinetic energy, where phi naught represents work function. Therefore phi naught equal to E minus maximum kinetic energy. Here maximum kinetic energy is known. Therefore first calculate energy of photon. Energy of photon, and energy of photon is given by E equal to hc upon lambda or h nu upon h nu, but here frequency is not given, lambda is given. Therefore E equal to hc upon lambda. Here h equal to 6.625 into 10 to the power minus 34, it is constant, and c is speed of light in vacuum, it is also constant, that is 3 into 10 raised to 8 meter per second, and lambda is given, it is 10 raised to minus 7, and we get energy in joules. But here kinetic energy, it is in electron volt. Therefore convert energy in joule to energy in electron volt, divide this by 1.6 into 10 to the power minus 19 coulomb, because we know that 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. Thus solving this we get 12.42 electron volt, that is energy of photon in electron volt. Now using Einstein's photoelectric equation, E equal to phi naught plus K maximum, this implies phi naught equal to E minus K maximum, and here energy of photon is 12.42 minus maximum kinetic energy, it is 7.7 electron volt, and we get 4.72 electron volt. Thus work function of silver when it is irradiated with a light of wavelength 1000 angstrom unit, a potential is 4.72 electron volt. The threshold frequency of a certain metal is 3.3 into 10 to the power 14 hertz. If a radiation of frequency 8.2 into 10 to the power 14 hertz is incident on the metal, predict stopping potential or cutoff potential for photoelectric emission. Here threshold frequency nu naught and incident frequency nu is given, and you are asked to calculate cutoff potential. We know that maximum kinetic energy is equal to h nu minus h nu naught, and also maximum kinetic energy is equal to AV naught, Hence EV naught equal to H in the bracket nu minus nu naught. Here phi naught represents stopping potential. Therefore phi naught equal to H in the bracket nu minus nu naught upon E, where E is charge on electron. That is equal to, here H is constant, its value is 6.625 into 10 to the power minus 34 in the bracket nu equal to 8.2 into 10 to the power 14 minus nu naught is 3.3 into 10 to the power 14 upon E equal to charge on electron 1.6 into 10 to the power minus 19 coulomb. Solving this we get 2.0292 volt. This is the cutoff potential for a given metal of threshold frequency 3.3 and incident frequency 8.2. Clear? Now next problem. The threshold stopping potential or cutoff potential for photocell for a light of wavelength 440 nanometer is 1.2 volt. 1.2 volt, it is the cutoff potential for photocell for a light of wavelength 440 nanometer, and you are asked to calculate threshold wavelength, and we know that K maximum equal to H nu minus H nu naught, but nu equal to C by lambda. Here nu is not given, nu or nu naught, therefore lambda is given and lambda naught is asked. Hence replace nu by C divided by lambda. Hence this EV naught equal to Hc upon lambda minus Hc upon lambda naught. Here H, C are constants, E is also constant, and lambda and is given, lambda not to be calculated. Therefore rearranging this equation we get Hc upon lambda naught is equal to Hc upon lambda minus EV naught. But we are asked to calculate lambda naught. Again rearranging we get lambda naught equal to, taking lambda naught in this side, then Hc upon Hc divided by lambda minus EV naught. Clear? Now therefore lambda equal to, here we can't cancel any terms, these common terms, because there is addition between these two terms, subtraction between these two terms. Therefore substitute all the values. Therefore H is 6.625 into 10 to the power minus 34 and C equal to 3 into 10 raised to 8 meter per second, and lambda is 440 nanometer. Nano can be written as 10 raised to minus 9 minus E, that is charge on electron 1.6 into 10 to the power minus 19 coulomb into phi naught, it is the stopping potential 1.2. Solving this we get 7.6589 into 10 to the power minus 7 meter. But here given wavelength it is in nanometer, therefore convert it to nanometer, and 7.658 can be written as 765.89 into 10 to the power minus 9 meter, or 765 nanometer. Clear? Stop the video and take it up. Thank you.